Hi everyone, my name is Celso de Oliveira and I'm a senior PhD student from the University of Connecticut working with Dr. Ramesh Malla, and we are researching about old railroad bridges, the dynamic response and structural response. So today I'm going to present my poster, which is a detailed final element model of Devon Railroad Bridge, East Abutment span, and the typical operation. Most of the railroad bridges in the United States were built in late 19th and early 20th century using outdated design codes and technology. For example, all those bridges that were built 100 years ago, the equipment was completely different. They used to be steam engines. Now we are dealing with electrical engines. The speed used to be different. Now we are dealing with a little bit higher speeds in comparison with the past. Although those bridges still operating under periodic inspection, usually they exhibit certain unusual behavior due to the wear and tear of the members, of the connection, all those things. And with approaching life expectancy of the most of those bridges, it's essential to establish methodology using 21st centuries like a computer simulation, field test data to better understand those bridges, those behavior, those structural behavior of those bridges, especially on the most modern passenger train. So what we did, we understand that if we create a model, the model will not fully represent the structure behavior, the current structure behavior, but will help us to understand what will be the perfect scenario. So by using the final element model, we assuming that's the perfect scenario. So the main objective is to create models that will represent that perfect scenario, and we can compare with the field test data. So for that study, we use Devon span 7, which is the East Abutment span. And Devon Bridge is located over Lower Housatonic River between Milford and Stamford, Connecticut. The bridge is a part of the Northeast Corridor, which is the busiest passenger line in the nation, and it's primarily operates under trains such as Metro North M8, Amtrak Acela, or Amtrak Regional. So we create a final element model using ANSYS Workbench to replicate that span. And the span is roughly 117 foot long. So what we did, we divide that span in 147. You can see in the figure 2 on the right side. We divide that span in 141 points, and then we move those series of loads step by step. For example, on that figure 2 on the right side, you can see it's a regional, Amtrak regional. Right now it's on step 92. So it's moving. Each time step is going to move to a different point. So methodology, we use a 3D model. We model our bridge using 483 members, all wire elements, with the 33 different cross sections such as I-bars, stringers, floor beams, diagonals, as you can see here. On figure 3, you can see the wire element means that it's just a member, and we assign a cross section, which is represented on the render, which is the figure 3 on the right side. We can see just the half span of that bridge. And we give special attention to the I-bar details because from the research and what we found on the field, the I-bars are not evenly loaded. Like, for example, the bottom I-bar right here in the middle, bottom chord, it's a 10 I-bars and they're all bundled together, but they are not uniformly loaded. Although in the design you assume that they're all taking the same stress, but in reality, some of them they'll take more stress than the other one. And we want to capture that information. So that's why we decided to give more details to the I-bars. So what's challenging, we have to go to the original drawings. For example, in figure 4, we have the 2 drawings. This is kind of the cross section. We have to go there to understand the spacing of the I-bars. The cross section of I-bars we found on the right side, right here. We got the length and the cross section. And we try to compile all that information and add to our model to be more realistic. Then the next thing we did is to represent the loads, which is the different trains. In this case, we use 3 different passenger trains, the most common ones. The red one on the left side is the M8, which is the Metro North M8 that goes pretty much all Connecticut and from Connecticut to New York. So the M8 it's electrical multiple, so meaning that you don't have a power engine, or each car has its own power engine. So basically the axle load will be almost uniform. They almost have the same axle load. That we can see a constant line here, which is roughly around 36.25 kips, if I'm not wrong. And then in the middle, on figure 5, we have the regional. Regional is Amtrak region. It's an intercity train that goes from cities, between, for example, New York to Boston or New York to Philadelphia. And usually this one has a power engine, which is the Siemens ACS 84, if I'm not wrong. And usually that has a higher load, which is around 52 kips. So we can see that the power engine is higher load in comparison with the coaches, which is 7 coaches and 1 power engine. On the right side, which is the Acela, it's considered our high-speed train. It goes from Washington DC to Boston and vice versa. Usual Acela, it has a 2 power engine on the left side and the right side. As you can see on that step force, we can see the 2 power engine has a higher load, and in the middle almost constant, but not exactly, because each coaches differ. You have a coffee, you have a VIP, and etc. etc. They change slightly, around 2 or 3 kips between the coaches. So we try to represent that information as well. And based on that information, we compare with the field test data. We collected some data using a laser Doppler vibrometer, and we convert that data to displacement time domain for certain points, and we use that data to compare with our model. And we use, for example, the train 3, it's regional, where we compare. We can see the red one is the static displacement. It's slightly less because of the difference of the speed. The blue one is the dynamic displacement, slightly higher in comparison with in the final element model. But the dash one, the black, it represents the field test. Few things we can observe from all the data. The middle one is Acela, the right one is M8. All the train visual, you can see the uplift right here. So meaning that, and the uplift happens when the train is outside of the bridge. For some reason, there is we kind of thinking that there is a lever effect that happens when the train is outside. It lifts a little bit of the floor system of the bridge. We found that in all the trains visual. And then another important thing is the point B, the magnitude from the entrance of the train, it's slightly different. As you can see here and here, the maximum load for some reason is not matching. We need to fully understand that behavior. And lastly, we were able to match the working frequency. By matching that working frequency, you can identify where the uplift is happening, where the maximum load is happening, all those things. That says, that's pretty much what we did so far. And the main advantage of a good final element model, it can help us to identify unusual bridge behavior that we might have. Like, for example, the uplift that we were not expecting. And we can see that the perfect world will be without, assuming that final element model is the perfect world, will be without the uplifting. And I want to say thank you for TIDC to partial sponsor this project, to Metro North and Connecticut Department to provide us the access to the bridge, the Polytech to provide us the equipment. And thank you, and I hope you enjoy my presentation.